So generally, if you look at our codes, they prescribe a relationship like this: Ft, the flexural strength, is some constant multiplied by your compressive strength to the power of n, where typically in, for instance, IS 456, what is the relationship? 0.7 square root of FCK. Okay, now quick question: what is FCK? Characteristic strength of concrete. Why do we call it characteristic strength? How do we define characteristic strength? What is the distribution we assume for concrete compressive strength? We assume a normal distribution, right? Okay. So this is what strength here? This is mean strength. Where is the characteristic strength? Is it more than the mean or less than the mean? It's here. That's FCK. So that this area is 5%. What does this mean technically? It means that if you test 100 specimens, right, only 5 or less should be lower than the characteristic strength, 95 should be above. Okay, that's the definition of characteristic strength. So when you design concrete in the laboratory, you design for the mean strength. So you have to add this value for doing the design. How do you know that value? In a normal distribution, you know that because of the standard deviation, right? In a normal distribution, you can estimate the mean from the characteristic value with a standard deviation. So in this case, the mean strength is FCK plus 1.65 sigma in a perfectly normal distribution. Now there are obviously distributions that may not be normal, but for compressive strength, it's hard to imagine that you will have a skewed distribution, right? If you take your marks in JEE or GATE, it's quite likely that you will not get a normal distribution. You may get a skewed distribution, right? Modulus, as I said, it's a material property. Very often we again take the help of data that is available to express modulus in terms of compressive strength. It's quite easy to do that. So as engineers, we would like to take things that are already available from literature. So all of these relationships, even this tensile strength relationship of 0.7 square root of FCK, there is no physical meaning of that, right? Why should one strength be related to square root of another? Doesn't make sense, right? So it's basically all data that has been compiled over many years, and people have taken advantage of the data to sort of prescribe this relationship that makes it easy in a construction project to proceed without testing the flexural strength directly. You can just do compression, which is very easy to do. Flexural strength, not everybody has the apparatus on site to do. Similarly, modulus strength itself people may have, but modulus, very unlikely that people will have the right apparatus to determine modulus of elasticity. In such cases, we often go with these prescribed relationships. For instance, the ACI relationship is derived from this principal equation where the modulus is expressed as some function which depends on the unit weight of the concrete and the compressive strength of the concrete. And actually our IS relationship of 5000 square root of FCK also owes its origin to this particular type of an equation. If you substitute your normal unit weight of concrete, which is how much? 2400 kg per cubic meter, right? If you use that value for unit weight, you will actually end up getting something like this. Of course, you need to do a conversion from your PSI. Here the unit weight of concrete is in pounds per pounds per cubic foot. So all very complicated relationships there. But nevertheless, IS basically gives you a simpler suggestion, 5000 square root of FCK, which is now going to go out of the window because new relationships are coming up based on data that has been recently collected. And this particular relationship is only valid for concretes of strength typically less than 50 or 55 MPa. Since we are using more and more of high strength concrete these days, there is a need obviously to come up with more suitable relationships that reflect what we are using today, right. For most concrete, modulus values will vary between 15 and 40 gigapascals. Obviously, the higher the strength of the concrete, the higher will be the modulus of elasticity, right. Poisson's ratio, we do not typically measure it, but in measurements that have been done, Poisson's ratio value for concrete has been around 0.15 to 0.22. You can determine it indirectly by testing both the modulus of elasticity and modulus of rigidity and using the simple constitutive relationship. In concrete, it is a little bit more complicated because you do not really have a clear zone of a linear stress strain relationship. It is not that easy in concrete, okay. Let me just anyway draw the stress strain relationship in concrete. So, typically you have sort of a linear behavior in the beginning, but mostly a non-linear behavior. You reach the peak stress and then there is some bit of ductility beyond the peak stress, okay. We do not call it ductility, we call it a quasi-ductile or quasi-brittle relationship in concrete. It is not like steel where you have a large extent of deformation that can actually happen. In concrete, there is some deformation that can actually happen. So, what we do is we take the initial about 40% of the load or 40% of the peak stress and define our modulus and all our other constitutive properties like Poisson's ratio within this loading area. What happens beyond is a highly nonlinear sort of a behavior which we do not really have the possibility to perfectly model and we can't really predict what is happening there, because of which the choice of modulus is only up to the first 40% of the load. Or if you go to the British standards, is even 33%. So, even there the relationship may not be perfectly linear, but if you test fast enough, you are likely to get a linear relation. Okay. So, because of the non-linear sort of a behavior, you do not have a distinct point where concrete is expected to yield. There is no yielding of concrete, okay. There is only failure, there is no true yield. In steel, you have a distinct yield point. Even in steels that do not exhibit that distinct yield point, you still assume that there is some strain level at which we can expect yielding to have occurred, right. What do we call that? Proof stress, right. We draw a line that is parallel to the initial linear portion wherever it intersects the curve, that is basically the proof stress, and we take that as the yield point, okay. Anyway, what happens in the long term is that concrete behavior is subjected to time dependent deformations, okay. Primarily it is because there is water inside the concrete and this water will move either when you keep the load on for a long period of time, just like the consolidation in soils, right. Why do soils consolidate? Because with the effect of the load over time, there is dissipation of the water that is underneath in the soil, okay. Similarly, in concrete, the longer you keep the load, the water inside the concrete tends to move around and that adjusts the structure of your concrete, okay. Because of this, design for creep becomes quite significant in structures that are expected to be dimensionally stable. For instance, if you have columns in tall buildings, right. If you have columns in tall buildings, ground story columns are typically expected to be high strength concrete. Now, if there is any change in height of the column over time, that is going to affect the way that the load is distributed across the rest of the building. So, it is very critical to define this extent of creep and have some means of actually measuring it properly. So, if you take a typical axial strain versus time relationship for concrete, you will, assuming you have a concrete column which is not subjected to any load, right. The water inside which is free now wants to come out, it wants to start drying, right. So, there is free shrinkage in the case of drying, okay. It is slowly drying out. Now, imagine one more column which is totally cladded, the column is totally cladded, there is no drying happening. In such a case, what is going to happen? You will not have any shrinkage, assume there is no shrinkage. What is going to happen then? Because of the constant load in the column, there is going to be some creep, okay. So, basic creep is defined as when there is no drying. Let's take a polymer. In polymer, there is no effect of drying, right? So, there is only going to be basic creep in that case. But in concrete, there is drying, which leads to shrinkage, and then there is load related effects, which we call as creep. Now, when both of them happen together, you can expect that you will get a strain which is the sum of your drying, shrinkage and basic creep. But in reality, you get actually a total strain that is greater than the drying, shrinkage and basic creep, and this is because of the presence of drying creep. In drying conditions, the creep becomes greater. Okay. So, in reality, let us say you take a metro structure, all the columns that are standing there, they are subjected to drying, they are subjected to a constant load. So, you have both the effects of drying and the creep, and this is going to lead to a sum total of the strain that is greater than the shrinkage and the drying creep basic creep that is determined separately. So, because of this, when you do determination of creep, and today the tall building code that is out for the last 3-4 years, the tall building code actually tells you that when your strength of the concrete exceeds 60 or 70 megapascal, ensure that you have done the right tests to determine the effect of the creep. It is no longer the creep coefficients that are prescribed in IS 456, they are not permitted to be used anymore. You need to start measuring, and that is where it becomes very critical to understand what is contributing to the overall deformation. Okay. So, but needless to say, the movement happens because of the presence of water inside. So, when I test high strength concrete, what is going to happen? Is the effect going to be small or big when I test high strength concrete? High strength concrete has lesser water, no? So, if there is less water in the system, there will be less creep, less shrinkage overall, okay, as compared to moderate or low strength concrete, your water is less. So, you will have less creep and less shrinkage, okay. Now, of course, in the beginning when you start loading, there is an elastic strain, immediate response of the concrete. If at any stage you unload the concrete, there will be an immediate elastic recovery. Whatever elastic strain has been induced will be recovered immediately. Incidentally, there is also a small strain that is recovered after that, which is called as a creep recovery, But even after removing complete load, you still have a permanently built up strain in the system, which will never go away. And because of this, creep and shrinkage can produce strains that are additive in nature, leading to a quicker collapse of your structure. Okay. This is okay in the case of a column, right? Column, you have compression, so it is shortening the column. You have shrinkage, it is also shortening the column. What about a beam? What is happening in the case of a beam? Let us say a simply supported beam is bending like this. The bottom is under tension. Because of the effects of the load, the tension is only going to increase, the creep is going to increase the tensile stress or tensile strain rather, right? Creep is going to add to the tensile strain. But what about shrinkage? Shrinkage is trying to push the member back. So, there the creep and shrinkage are acting in different directions. So, depending upon the geometry of your structure and the way that the load is acting, you may have creep and shrinkage either acting together or opposite. Consider a pre-stressed beam. What is happening in a pre-stressed concrete? You have steel which has been pulled and concrete that has been pushed. So, what is going to happen with time? Loss of pre-stress will happen. Why? Because steel initially was subjected to a particular level of tensile stress. It is relaxing with time. Steel starts relaxing. You have seen this, right? When you tie a string, with time it starts drooping because internal stress distribution happens. We call it relaxation, because of which that loss in the stress is happening inside. When the steel loses stress and the concrete starts creeping, you will have a loss of pre-stress. So, in pre-stress members, creep and shrinkage are going to be extremely critical to analyze and design for, okay. And structures like tall columns in tall buildings are again going to be subjected to very high levels of creep and shrinkage. Right. So, again we talked about this already, so I am not going to discuss this again. Now, coming to the other long term aspect of concrete, it is durability, okay. You design concrete considering the types of materials to be used and the process of actually putting the concrete together, which includes mixing, transportation, compaction, curing, temperature, and ultimately the workmanship, right. All of that goes into actually describing the properties of the concrete. If you do not cure well enough, as we discussed earlier, strength may not get affected significantly, but the curing is definitely going to get, curing is definitely affecting the durability of the concrete. Now, there is also the consideration of the type of environment, and that dictates the type of processes that lead to deterioration. If you are in Chennai, what is the environment? What kind of deterioration you expect more? Chennai is a coastal city, so you expect corrosion, right. Corrosion of reinforcement is going to be primarily driven by chlorides, which are present in the seawater or in zones slightly away from the coast, the airborne salts that are taken up by the winds, which will deposit the chlorides into the concrete, and that will ultimately drive the corrosion of the steel. If you go further inland, you do not have any chlorides, but then atmospheric carbon dioxide can penetrate the concrete and lower the pH of the concrete, causing corrosion. So, all of those things you need to understand and design for. There are physical mechanisms and chemical mechanisms. Abrasion, where do you need to design for abrasion? Abrasion of concrete. Pavements or aircraft runways, okay, you need to design for abrasion resistance of the concrete. What about erosion and cavitation? Dams, right, because when the river is in spate, it will carry huge rocks and boulders also along with it. So, all that goes over the spillway and falls on the concrete, and you really need to be worried about what is going to happen. Cavitation of course happens because of the drop of water and the bubbles that finally end up bursting, and that can create significant pressures that can damage your concrete. So, durability is basically defined as the ability of concrete to withstand deterioration, okay, all kinds of deterioration. These are not load related, mostly they are environment related. That is the distinction between a structural loading related problem or a durability related problem. So, durable concrete is expected to retain its original form, quality and serviceability when exposed to the environment. So, we design for concrete durability based upon the environmental service. When we design in Chennai, the considerations will be different as compared to designing in Bangalore, right, because we have different mechanisms acting in different locations. Now, if you look at most durability problems, you will see that they are resulting in manifestations that are not all that very different. Most of these problems will relate to some gradual deterioration or erosion of the surface of the concrete, slowly losing mass from the surface. Alternatively, many other durability problems may lead to expansion or volume change of the concrete, okay. Now, of course, volume change also happens in creep and shrinkage, but we do not consider that to be a durability issue. Truly speaking, everything happens together, but durability is taken as the effect of the environment. And here, volume change can either change the volume of the paste or the aggregate or the steel. In corrosion, steel volume also changes, but that leads to cracking in the concrete. So, all of these have to be assessed separately and designed against. But if you look at all the common durability problems in concrete, including corrosion, sulfate attack and chemical attack, alkali aggregate reaction, freezing and thawing, the one common feature to all of these is, what is common to all of these? Or to ask you in a different way, can any of these happen without water? No. Why? Because corrosion of steel, you need moisture for the reactions to proceed. Freezing and thawing obviously is the penetration of water, conversion to ice and so on. Chemical attack can only happen when the water penetrates the concrete with the salts that damage the concrete. Alkali aggregate reaction, the expansions happen because of the imbibition of water. So, without water, you do not really have a durability problem. So, generally water is either involved in the reaction or is necessary for the manifestation to occur. So, because of this, If you keep concrete dry throughout its lifetime, you do not have a durability problem. If you keep concrete water resistant for a longer time, you do not really have many of the durability problems. Okay. So, very rarely you will have a problem created because of factors other than water. So, because of this we design concrete to be watertight or impermeable, sorry, yeah. So, durability is generally measured in terms of the permeability of the concrete. The more permeable the concrete, the less durable it is going to be. That has been the primary basis for defining the durability test methods that are typically carried out. Okay. We do not usually test the actual performance in different environments because each test may take several months to some years to actually perform. So, because of this we define the concrete quality in terms of its impermeability measured by different means, and we use that as an estimate of concrete durability. Okay. So, with that we finish our discussion of an overview of cement and concrete. From the next lecture onwards, that is tomorrow, we will start talking about the chemical admixtures. Okay. So, we will finish with that for today.